Welcome back to ECE 320A. We're still in Unit 6, but this is getting near the end of Unit 6, so you should be well on your way to finishing up homework number 6. And you should now be completing Chapter 12, which is dealing with Laplace transforms. And in this video, what we want to show is how we've actually been able to sort of come full circle or do a lot with the techniques and skills that we're developing relative to Laplace transforms and inverse Laplace transforms. We'll carry those even further in subsequent material, but now we can actually start to have quite a bit of fun with analyzing. Well, maybe fun is relative and maybe it depends on your perspective, but let's assume now that we're going to have fun doing some circuit analysis using Laplace. And today what we want to do is what I've indicated here under our goal section, and that is to find a transfer function of a circuit. And once we've found the transfer function, then we can actually start applying all types of inputs to that same transfer function or that system. We don't have to rederive the transfer function each time we want to examine the behavior of that system due to a changed input waveform. We can simply use exactly the same transfer function. Obviously, our input has changed, but once we find the Laplace transform of this new input, then we can find the total output Laplace transform expression, inverse Laplace transform, and find the exact solution to the problem at hand. And we will also be able to look at poles and zeros, check our answers with the final value theorem, the initial value theorem, if appropriate. So let's get started and see the fun that we can have with Laplace transforms. It doesn't take a complicated circuit to illustrate these ideas, and for that reason, let's go ahead and go back to a trusted circuit. And at this point, you should feel very comfortable with this RC circuit. And what is it in terms of its circuit behavior? Well, the output voltage across that capacitor is a low-pass version of the input waveform V sub I of t. And the bandwidth or the properties of that low-pass filter obviously depend on the particular values of the resistor R and the capacitor C. And you could play with R and C and obtain different bandwidths or different frequency responses for this low-pass filter. They would all have the same low-pass filter shape. It's just how many or what range of frequencies would be passed would depend on the values of R and C. What we've learned so far is how to move from differential equations to Laplace transforms. So let's now attack this circuit analysis problem by finding the differential equations or the governing equations that represent the dynamic behavior of this circuit. And you can do that many different ways, and you should have consistency between those ways. If one student finds it using one approach and another student finds the governing differential equation using another approach, you should see consistency between their final sets of expressions that govern the dynamic behavior of this circuit. And let's illustrate that. But before we do that, what should we probably, in terms of variables, we have a lot of variables here. We have an input variable, V sub I of t. I've already indicated a current in that circuit. We have the voltage across the resistor. We have the capacitor's voltage. We have the resistor's current. We have the capacitor's current. In fact, those are the same because it's a series circuit. But what should we probably focus on if we're trying to find a dependent variable? Our independent variable in this case is V sub I of t. That's going to be given to us. That's what we will assume we have the ability to specify or use. What we want to do is now say, how does the circuit respond in response to a particular chosen value for V sub I of t, the input voltage to this low-pass filter? First off, is it going to be a differential equation? Or step back again, do we have any energy storage devices? If that resistor and capacitor were now just a resistor 1 and a resistor 2, this would be an instantaneous circuit and there would be no energy stored in that circuit. But since we have a capacitor, that capacitor has a differential relationship between the current and voltage of that capacitor, and that produces some dynamics or memory, and so we do have some dynamic behavior. We should be expecting a differential equation. We have one energy storage device. We should be expecting a first order differential equation for this low pass filter. And with that being said, what is our energy storage device? Our energy storage device in this particular circuit is a capacitor, and because of that, we know Eli the Iceman. Now we're focusing on the second acronym in that expression, which is ICE, which is the capacitor relationship between current and voltage. And now, based on that three-letter ICE acronym, we focus on the last variable, which is E, which is corresponds to the voltage. So we should be focusing in this particular circuit on the capacitor voltage in writing our differential equation. And that's all just because, oh, we have an energy storage device. Oh, that energy storage device is a capacitor. I is equal to C dV dt. dV dt, that's the differential. Oh, we probably need to focus on the voltage of that capacitor. That will now allow us to obtain our differential equations. Let's now write, suppose I know that when you're first learning circuit analysis, you really like to use mesh analysis. So suppose you do write KVL. Now you have minus V sub I plus the voltage dropped from left to right across that resistor, which is Ri of t, plus V sub C of t. But we said we want to write the equations or equation in terms of capacitor voltage. We have the independent variable, which is V sub I of t. We have capacitor voltage, but we also have another independent variable, or a dependent variable there, I, which we don't want. But again, we can fall back on ICE, and that gives us, since the current through the resistor is the same as the current through the capacitor, we can now eliminate that resistor current by re-expressing it in terms of a variable that's associated with the capacitor voltage, and in particular, because of ICE, C dV dt is now what we will use to express the resistor's current. So everywhere we see the I, we can now replace that I with C dV sub C dt, and now we have one equation. It's a first order differential equation that consists of capacitor voltage and its derivative, and the independent variable, the voltage source, V sub I. So, writing KVL, which is a standby, we could have found a first order differential equation. What if, when looking at this circuit, somebody said, I want to actually write KCL at node A. I want to do nodal analysis. That is equally valid, and in this particular case, it may even be more direct. So now let's say that we write KCL at node A. Then what happens? Well, if we write KCL at node A, we're now saying that we're interested in the resistor's current I sub R, and the capacitor's current, I sub C. There's nothing flowing here. So the sum of those currents exiting node A need to sum to 0 by Kirchhoff's current law. If we can now find a expression for the resistor current in terms of V sub C and V sub I, and an expression for I sub C in terms of V sub C, think ICE, then we'll have another way of computing or finding the governing differential equation. I sub R, in this case, we're interested in the voltage dropped from right to left, positive to negative. We have on the right side of that resistor a voltage V sub C. On the left side of that resistor, we have a voltage V sub I. The difference then is V sub C minus V sub I in that direction from right to left. If we divide that by R, that gives us, by Ohm's law, the current I sub R going to the right, or I'm sorry, going to the left through that resistor R. Or KCL at A now says that we can find that by writing V sub C of t minus V sub I of t over R plus, now the capacitor's current is just from ice, C V sub C prime of t, and those exiting currents from node A need to sum to 0. Now we can multiply both sides by R. R is a given positive number, and that now allows us to rewrite that as V sub C minus V sub I plus RC V sub C prime equaling 0. And hopefully you can see that the equation in the blue box is equivalent to the equation in the black box. So whether you wrote a KCL equation or a KVL equation, it doesn't matter. It should result in the same governing differential relationship. And it's a first order differential equation because we had one energy storage device. That energy storage device was a capacitor, so we're focusing on the voltage from ICE, which is that third variable in that acronym, and or third, yes, constant or letter in that acronym, and that then allows us to focus on the voltage. Let's now Laplace transform this differential equation. V sub C of t, little v sub C of t, is an unknown, but we will be able to specify it, independent variable. So let's just say that we can find its Laplace transform, and we'll call that capital V sub C of s. Laplace transform of little v sub I of t is capital V sub I of s, and the Laplace transform of the derivative of v sub c prime, which gets scaled by RC, is just s times the Laplace transform of v sub c of s minus the value of the time domain voltage across that capacitor evaluated at t equals 0 minus. There now we're in the frequency domain. So we've gone from the time domain. Now you can run across the room and be in the frequency domain, and now we can start playing with the frequency domain equations using algebra in terms of these polynomials in S. And to do that, we are actually wanting the transfer function. We want to find what's the transfer function between the input signal, V sub I, and the output signal, which is corresponding to the capacitor voltage, V sub C. Since we're wanting the transfer function, we don't need to worry about transients, so let's just neglect the initial conditions, or we can let the initial conditions equal 0. In so doing, we just set V sub C of 0 minus equal to 0. We can now solve this equation. Now this particular equation has 3 terms. Let's isolate or combine the V sub C terms, and let's combine the V sub I terms and put them on different sides. There's only one V sub I term. Let's add that to both sides. It now appears by itself on the right-hand side. And we can combine the coefficients that are scaling the Laplace transform of our capacitor voltage, and we have SRC plus 1. And that is consistent with what we would expect. We had a first order differential equation. We should expect a first order transfer function, which is what we will find when we start taking the ratio of the output voltage to the input voltage. But right now we have this polynomial equation that has a polynomial in S scaling V sub C and a coefficient of V sub I. In this case, it's a polynomial of S where it's constant, and that constant is equal to 1. Let's now divide both sides by SRC plus 1, and let's divide both sides by V sub I of S. Or, in other words, we're going to end up with, on the right-hand side, 1. On the left-hand side, we didn't touch V sub C, but we did divide by SRC plus 1. And we did divide by V sub I of S. So V sub I of S ends up in the denominator on the left-hand side, and SRC plus 1 ends up in the denominator of the right-hand side. And we now have our transfer function. Here is our transfer function for that first order low-pass filter. The transfer function is between the input signal, and here the input signal, we have its Laplace transform in the form of capital V sub I of S. So this is now the transfer function between the input signal V sub I of S. So here, let me go ahead and make this connection between the input signal V sub I of S and the output signal V sub C of S. I was calling that the capacitor voltage, so I had a subscript of C. So that's now V sub C of S. So the output signal is in the numerator of our transfer function ratio of output to input. That now gives us our transfer function, which a lot of times we will simply express or label as a variable capital H of S. So now we have, if we multiplied back through by V sub I, we also have another way of connecting the output to the input. We now have the output signal is equal to the product of the transfer function, that's our low-pass filter, H of S, with the input signal's Laplace transform V sub I of S. Suppose in this transfer function, right now it's just a function of arbitrary values of R and C. Just to give us something to play with, suppose that we let that RC product equal 1/10 or 0.1. So now the transfer function becomes H of S is equal to 1 over 1/10 RC S plus 1, and this particular structure for the transfer function is labeled a particular name, or given a particular name, and this is now a time constant form where this variable, weighting the frequency variable S, is our time constant tau. So here we have tau S. Our S is in radians per second. This is a time then in seconds, so that we have radians for our units on the product of tau S. So tau is now our time constant, and that's explicitly visible. Our time constant is 1/10, and in this case we have 1/10 S plus 1 in our denominator. We could also factor out that time constant tau, and now the 10 in the basement of the denominator floats up to the numerator, and in this right-hand side expression, which is equivalent to the time constant form, is another form that we call the pole zero form of our transfer function, because now we can explicitly see the pole factors and the zero factors. They've been explicitly factored out so that here we see that we have a pole at minus 10. Relative to this time constant form, we know what? If we wanted a 1% settling time corresponding to 5 time constants, now we have 5 times 1/10, or in 1/2 of a second, we would have actually reached our final value. So it doesn't take us very long, 500 milliseconds, a half a second, to reach our settling time, or to be to a steady state condition for this particular transfer function, or this low pass filter circuit, this RC circuit that has a time constant or an RC product of 1/10. Let's now look at, now that we have all these different forms, we can start identifying poles and zeros. What can we say about the zeros? What values, and let's just talk about the finite zeros. What finite values of S cause this numerator to vanish or equal 0? Well, there are no S's in the numerator, so in fact we have no finite zeros. What about poles? Well, we better expect some poles. We had a first order system. We had one derivative in our time domain expression. That led to a first order denominator. So we should have one pole, and we do. We have one pole. We can now find one value of S that causes that denominator to vanish, and that pole is now at S equal to minus 10. What we want to do now is look at what happens to this circuit. Now that we have the transfer function, we can start analyzing this circuit's behavior for many different kinds of input waveforms. Let's look at one. Let's look at a few, but to start with, let's look at a constant input. Suppose somebody now applies a constant value of 5 at time 0 and leaves it at 5 for time to infinity. What's the Laplace transform? Or we could write this as 5u of t, and now maybe it's easier to think about what the Laplace transform of little v sub I of t is. Now it's just a scaled version of the Laplace transform of a unit step, and the unit step has a Laplace transform of 1 over s. And you could go back to the definition, you could look in your tables, but at this point you should be starting to almost immediately recall the Laplace transform of the unit step is 1 over s. V sub I has that amplified by 5, meaning capital V sub I of s is 5 over s. Now we can actually find a transform expression for the output voltage's Laplace transform, which is capital V sub 0 of s. That's h of s, the transfer function, which is actually 10 over s plus 10 times the input's Laplace transform, which is 5 over s. But now you should almost be instinctively starting to feel what you want to do with that capital V sub 0 of s. You want to find what's the time domain waveform for the output voltage across that capacitor. Well, here we have a second order denominator, and that means that, we can now do a partial fraction expansion. You should see now that you have a pole at the origin, or at s equal to 0, so we have one term, a over s, plus b, And our second partial fraction expansion term is b over s plus 10. We can use the cover-up method to try to find a and b because they're distinct roots of our denominator polynomial. A is now scale both sides by s and let s go to 0. We now have in the numerator 50. Downstairs we have s plus 10. We let s equal to 0, or a now becomes 5. B, we scale both sides by s plus 10, and we evaluate the resulting expression, which is now 50 over s, at s equal to minus 10. We now have b equaling minus 5, or 10 divided by 50 divided by minus 10. Or what is v sub 0 of t? Now we simply need to inverse Laplace transform those two frequency domain expressions and scale those by 5 and minus 5 respectively. Well, a over s is just a constant scaled by a, so now that gives us in the time domain a value of 5, and a 1 over s plus 10, that's a exponential, no oscillation, just an exponential of minus 10t. So now we have minus 5 scaling e to the minus 10t, and that's true for t greater than or equal to 0. That's now what happens when we inject a step of magnitude 5 into a low-pass filter that has an RC, or a time constant, of 1/10. And from this v sub 0 of t, you should be able to find what's going on for all values of time. Where do we start? And where do we end up? We could do that by just looking at limiting values on time in our v sub 0 of t expression. And we could check those against the final value theorem and the initial value theorem. The final value theorem, we need to look at s times v sub 0 of s and make sure that we have no poles on the imaginary axis or in the right half plane. The s cancels the s in the denominator, and so now we're okay with the s v sub 0 of s product. So we can apply the final value theorem. The final value theorem allows us now to say that the limit as t goes to infinity of this output voltage v sub 0 of t is now v sub 0 of infinity, which is the limit as s goes to 0 of s v sub 0 of s. But what is that? Well, now that's the limit as s goes to 0 of s times 10 over s plus 10 times 5 over s. These s's cancel, and now when s goes to 0, we have a well-behaved denominator, we have an okay numerator, we have 5 times 10 upstairs, or 50. Downstairs we have 10, so we're saying that we should end up at 5 as t goes to infinity, and in fact, as t goes to infinity, we see that the exponential term vanishes, and indeed we do go to a final value of 5. What about the initial value theorem? Here it's not as challenging to apply this because now all we have to do is see if the limit exists. So now as t goes to 0 plus of v sub 0 of t, that's now v sub 0 of 0 plus, which is the limit as s goes to infinity of s v sub 0 of s. But that's now just the limit as s goes to infinity of s times h of s, which is 10 over s plus 10, times v sub I of s, which is 5 over s. Now we have the limit of s over s squared, or basically 50 over s s is going to infinity, that actually is going to 0, and that checks with what happens with v sub 0 of t when we replace or substitute t equal to 0 into that expression. We have 5 minus 5 or 0, which means this low-pass filter, if it's not energized, if that capacitor is unenergized to begin with, and we turn on a step at time t equals 0, then initially there's no voltage across that capacitor. And eventually that voltage will build up to a value of 5, and it builds up through this exponential decay. And so now you can imagine what this v sub 0 of t waveform looks like as a function of time, all based on a little Laplace transform analysis. As I said, as long as we now have the transfer function, we can start looking or examining many different possibilities for the input waveform. Suppose we look at a sinusoidal input. What's the Laplace transform of a cosine, a pure cosine, no exponential damping? We have a weighting of 4, and the cosine is s over s squared plus omega squared. So that now, if we want the output voltage, v sub 0 of s, we now scale the transfer function, 10 over s plus 10, by the transform of the input, which is 4s over s squared plus 3 squared, or 9. And now you should be able to immediately write down the partial fraction expansion expression associated with the output voltage's Laplace transform. We have 3 poles. 1 is real at minus 10. 2 are purely imaginary at plus and minus j3. Or we now have an a over s plus 10. We have a b. Let's say that's weighting the cosine expression. And let's say we have c weighting the sine expression. What's the structure of v sub 0 of t? Well, now you can inspect that or write that down by inspection of capital V sub 0 of s. We have a that's weighting an exponential with an exponential decay of minus 10t. We have b weighting a cosine, and we know the frequency of that cosine, that's 3t, plus c times the sine of the same frequency, 3t, and that's true for t greater than or equal to 0. Now, if you were lazy, or if it was a Friday night, or you were wanting to show off your calculator to your roommate, you could say, oh, I can find A, B, and C on my calculator. And you actually can. You could do an expand and say 40x, since what do we have here? We have 40s, so I'm just using x because that's easier for me to plug into my calculator. Not really, but let's just assume it is. Then we have x plus 10 times the quadratic, which is x squared, x caret 2 plus 3 squared, or 9. And now we just close everything up. And this now will actually expand to give us 400x over 109 x squared plus 9 plus 360 over 109 times x squared plus 9 plus, in fact, it spits out a minus sign, so let me go ahead and put a minus sign, minus 400 over 109 x plus 10. And if you wanted to, now you could very easily take this into the time domain. V sub 0 of t, now this is our pure cosine. This is not quite our pure sine. We would need to rewrite 360 as 120 times 3. That's now our pure sine. And this is our exponential with a weighting of e to the minus 10t. Or we now have 400 over 109, so about 4, cosine of 3t, plus almost 120 over 109 sine of 3t, minus, again, almost 400 over 109, e to the minus, I'm getting 4s are wild, but now we have an exponent of 10t, and that's t greater than or equal to 0. If you didn't want to get this exact answer, and you simply looked at this capital V sub 0 of s, what could you say about its limiting values? What's it going to start at as a waveform at time 0 plus, and where is it going to end up as we march off to infinity in time? Well, hopefully, as you march off to infinity, you can see that, oh, we have a sinusoid that's driving this system, this linear system. It's just going to continue to oscillate at the frequency that we're shaking it at, which is a frequency of 3 radians per second. So we aren't going to actually reach a final value theorem. In this particular case, the final value theorem does not apply. And does that make sense relative to what we just found for our V sub 0 of t? As t goes to infinity, the exponential term vanishes, but we're still left with a sine and a cosine at 3t, or as a frequency of 3 radians per second, which is the frequency of our input that we excited the system with. So yes, we now just have this sinusoidal waveform going and going for V sub 0 of t. Can we apply the initial value theorem? That we can if the limit exists. And now we're looking at the limit as s goes to infinity of s, which in this case we have 40s times s. We have 40s squared over s plus 10, s squared plus 9. Or we have a cubic downstairs, we have a quadratic upstairs. We now have a net something over s, and as s goes to infinity, that goes to 0. So at 0 plus, we're saying that this circuit starts at 0, and that makes sense because we had an unenergized low-pass filter. We apply a cosine waveform at time t equal to 0, but the voltage is not going to change instantaneously across that capacitor, so it stays at 0 at 0 plus, and then it starts shaking, and it will have a transient that lasts, what? Basically a half a second, because our time constant was 1/10, and we take 5 of those 1/10ths, or 5/10ths, in a half of a second. That third term in this expression for V sub 0 of t is gone, and we're now just left with these shaking cosine and sine, or we could combine that into a single cosine waveform with a phase shift. So this makes sense that we're starting at 0, and then we just oscillate back and forth as time evolves towards infinity. And now we can see that we can do a lot of analysis with the machinery that we now have in the form of Laplace transforms.